All right, welcome everyone. It's my pleasure to announce Sasha Philippov. Sasha is a professor at the University of Maryland, and he's the deputy director of the Simons Collaboration for Extreme Electrodynamics of Compact Sources that we also have some people working on here at University of Toronto. Sasha did his PhD at Princeton University, and then he was a Hubble Fellow at Berkeley, and then he was a faculty member at the Flatiron Institute in New York before he moved to Maryland. And there he was also my advisor, and I was his first postdoc, actually. So it's particularly my pleasure to welcome Sasha, and he will tell us about neutron stars and black holes. Sasha, take it away.
All right, thanks so much, Bart, and thanks so much, everyone, for coming here. So indeed, I'm going to tell exactly two stories about two separate class of sources. One of them being neutron stars, the other one being particular class of black holes and how they produce non-thermal light that we see here on Earth. So before I go here, I want to thank all my collaborators, students and postdocs who worked with me over significant time, and particularly Simons Foundation, who sponsors our collaboration. And for undergrads here, I want to advertise our summer school and research experience happening this summer. If you're interested in any topics ranging from plasma physics, controlled fusion, laser plasma experiments, extreme astrophysics, please consider applying to our school. We'll have 2 weeks of lectures covering a broad range of topics related to the science, and the expectation is that the students would go on to do research experience at partnering institutions for another 6 or 8 weeks. So if either you're interested or if you know someone interested in this, please consider applying or let me know if you have any questions. So after that, I want to quickly motivate why this is interesting to look into these things now. Neutron stars have been discovered in the 1960s, black holes around the same time. So it's been roughly 60 years since we as human civilization are thinking about these objects with observations. So it's reasonable to ask why now. So why now for neutron stars has been a huge revolution in the last 10 or so years, because we are discovering considerably different classes of objects and considerably different phenomena that these neutron stars are producing. The most striking one is the fast radio burst. This is the phenomenon of very bright radio emission lasting about a millisecond coming from cosmological distances. We are not sure whether all of them are connected to neutron stars, but around the start of the pandemic in 2020, there was a phenomenal discovery of one particular radio burst associated with an X-ray flash coming from a highly magnetized neutron star in our own galaxy. So that gives us confidence that at least some of the sources are related to neutron stars, in particular these objects called magnetars, which are the most magnetized neutron stars that we know in the universe. The more regular neutron stars that we call pulsars, is our regular rotating neutron stars with slightly lower magnetic fields, also undergo revolution in the last 10 years because we are not studying them just in one band as we did for 60 years, but we are also looking them at much higher energies. So these are two particular examples. This is an observation by a nicer X-ray mission at the International Space Station, which monitors thermal X-rays of a particular class of neutron stars, millisecond pulsars. And what it uses it for is to infer the equation of state of dense nuclear matter right in the core of the neutron star. So how they do this is they monitor light curves in thermal X-rays that are produced by energetic particles that are bombarding the stellar atmosphere. And once they're bombarding the stellar atmosphere, they produce hotspots, which are then rotating on the surface of a neutron star. And that experiences a Doppler effect because the star is spinning with very high velocities, and gravitational effects because the neutron star is massive. These effects are imprinted in the light curve that the satellite detects. And that allows to infer the mass and radius of a neutron star just from this particular observation. The other one is much more recent. This is coming over about a year from now. And from these observations, we got to know that neutron stars can accelerate particles to Lorentz factors exceeding 10 million. And how do we know this? Is because we discovered that the particular pulsar Vela is producing tera-electron volt emission, in this case exceeding 20 tera-electron volts. So to get these photons, you need to have particles. Those energies are exceeding the energies of the photons that we detect. And if you remember that the rest mass of the electron is half MeV, you can compute how much Lorentz factor you need, and that would be exceeding 10 million. So they're very efficient particle accelerators. What unites all of these topics is that all of this radiation is produced by very underdense, very hot plasma, very relativistic, accelerated to high energies that are producing these broadband emission signatures. To understand any of this observation, you need to understand how the physics of collisionless relativistic plasmas work out. And why this is complicated is because these plasmas are collisionless, they're not really colliding charged particles between each other because the density is so low and the temperatures are high. And instead of interacting via basically, Coulomb collisions between the particles, the rule of the game here is that each particle creates electromagnetic field and every other particle creates electromagnetic field. And then each particle basically interacts through all the particles in the system. So there are collective electromagnetic fields that are determining the dynamics of the system. And on the black hole end, there has been a revolution in the last 7 years or so. It started with a gravity interferometer. This is a near-infrared interferometer that was able to localize a hotspot orbiting around the black hole in the center of our own galaxy. So this is a trajectory of a hot blob of gas moving around the Sagittarius A star, our supermassive black hole, at a distance comparable to 5 to 10 gravitational radii from the center of the black hole. So we are able to understand the dynamics of the plasma on extremely small scales, very close to the center of the black hole. And that got escalated with the Event Horizon Telescope. This is an array of radio telescopes spanning the whole globe that had enough angular resolution to image the radio emission around the supermassive black hole in our own galaxy. And in the M87, these are two big black holes. One is of the mass of few times 10 to the 6 solar masses, and another one comparable to the billion solar mass. It's further away in M87, but its mass is bigger, so the angular resolution on Earth is actually quite comparable. And both of these images basically are shaped by gravity of the supermassive black hole, the rotation of the gas around the supermassive black hole, and the plasma physics. So the first two effects are particularly simple to understand because GR is so good theory for explaining everything that we know so far. The Doppler boost effect is also quite simple, but how the electrons are actually energized to produce the light that we see is far from certain. And that's where the plasma physicist interest comes in. And the third class of objects that are picking up really recently are observations by IceCube, the neutrino observatory at the South Pole that is basically aiming to understand how neutrinos are produced in the universe. And the most efficient way of producing high-energy neutrinos is to accelerate protons. If you're able to accelerate protons, you can collide them with X-rays, or you can collide them with other protons. And in the process of doing so, you would produce pions. The pions would decay into gamma rays and neutrinos. And neutrinos, as they weakly interact through matter, could reach you as an observer on Earth. Something may happen with gamma rays on the way, and this is particularly interesting in some of these observations, that neutrinos seem to arrive alone without the accompanying gamma rays. So this is a puzzle that people are interested in, but again, at the ground truth, the center of this problem is to how to accelerate these relativistic protons. So the broad theoretical approach is like a very big scale picture that I want you to think right now is that you can model the plasma around the sources with varying degrees of approximation. And the first theory that I like to think about is what's called force-free electrodynamics, which I call a plasma without the plasma, and you'll understand why. So the plasma physics in a very strong magnetic field is quite simple. The only effect that is very important to think about is if you put electric field into the plasma, the pair of two oppositely charged particles will separate. The positive charge will go along the electric field, the negative charge will go against the electric field. It would create an electric field that would like to cancel the electric field that I created in the first place. So once you do that, the rule of the game is that the electric field parallel to the magnetic field has to vanish. Full stop. So that has to be zero. And just from that simple equation, turns out you can determine the current that the plasma has to drive in order to satisfy that. Once you have a current, you have the full Maxwell's equations, right? You have two evolutionary equations for the electromagnetic field, the prescription for the current, you can run away with this and produce the dynamics of the electromagnetic field. And that's what we do usually when we study things like neutron star magnetospheres. The motivation there is that the field around the neutron stars are ridiculously high, 10 to the 12 Gauss and higher, and the magnetic field energy dominates. The other interesting region is this region of a relativistic jet. This is an outflow from a supermassive black hole that is dominated by the magnetic field energy from the surrounding plasma. So this is a broad scale picture. This is a supermassive black hole. This is a plasma accreting onto this black hole. And this white region is basically the huge relativistic jet that comes out. And I'll come to this physics later. And in this jet, the density of the plasma is very low. The magnetic field is very strong, and it is governed by the rules of this force-free electrodynamics. The problem comes in when the plasma is not guaranteed. And that happens around neutron stars. The plasma does not just come out, and as you'll see later, comes self-consistently from quantum electrodynamical reactions. So these reactions depend on electric fields that are not screened by the plasma, as you will see later. The second place where it breaks, and this is a big topic in what we typically study, is when the magnetic field would like to go through zero. So if you can imagine field line going this way and you have another magnetic field line going the other way, if you squeeze them together, the magnetic field would have to go through zero. And when the magnetic field goes through zero, you can no longer assume that the magnetic field energy dominates over everything else. So the moment that happens, you have to turn on the plasma. And why it happens is because the energy has to go somewhere, and it obviously goes from the magnetic field into the particles. So the first order effect is to say that all of this magnetic energy gets annihilated into the plasma pressure, and you have to include it into your equations. And that's the next step, which is called magnetohydrodynamics, which is basically a theory for 8 equations for 8 variables. You have the density of the plasma, pressure of the plasma, 3 components of the velocity of the plasma, and 3 components of the magnetic field. And you have conservation laws, conservation of mass, momentum, and energy, and you have the Maxwell's equations, and you can solve the systems consistently. So this gives you a good approximation, even in things like this current sheets, where magnetic field goes through zero and intense currents have to flow. There are disadvantages, is that when you derive this set of equations, you do assume that the plasma is a collisional fluid. You have to assume thermal equilibrium in order to come to these equations. And the thermal equilibrium in this charged systems of charged particles are necessarily realized only when the particles are efficiently colliding with each other. So when this happens, you have to assume, for example, that the plasma maintain a pressure that is the same in all directions, which you could think may not necessarily be true if there is a strong magnetic field. It would have to exert some preference for particles going along or perpendicularly to the field. It also doesn't include things like heat fluxes, because fast particles can go along the field line and equilibrate the plasma temperature, for example. These things are also not included. And moreover, what it doesn't include is a particle acceleration. Everything is a Maxwellian, so you assume that the distribution function is a nice peaky function at a certain temperature. And this is not very consistent with what we see in the universe. What we see from the source is a non-thermal distribution. So as you saw, for example, in the spectra from the Vila pulsar, there was a broad power law around the GeV energies, and then another bump at another energy. So that necessarily means that there is a broad distribution of energies of the particles, and this is not described by magnetohydrodynamics. And if you want to go first principles, as you all know, you go to kinetic physics. Kinetic physics describes the self-consistently evolution of the distribution function of the plasma, in this case, under the action of the electromagnetic field. The benefits, of course, are that you include all the physics. The shortcomings is that if you want to solve this on the computer, this may have too many scales to worry about. And obviously here there are scales coming from the size of the object. In the case of a neutron star, this is something like, the star is 10 kilometers. The size of the magnetosphere is thousands of kilometers. But the action happens sometimes on scales of few centimeters. On this few centimeter scales, the electrons are bouncing and positrons are also bouncing to basically screen the electric field in the whole magnetosphere. So once this broad separation of scales gets involved, it gets complicated, and there is no unique solution to these problems. So you have to basically work out a set of approximations that span all three of those or two or something like that to describe phenomena happening at every scale. So this is just to iterate, why do we need this? We need kinetic physics and not just MHD in some cases, because we need to explain power loss, which means we have to explain observables. And that's how I motivate this in an astronomy colloquium. This is a physics colloquium, so I would like to go more theoretical. The first theoretical motivation would be that, this collisionless plasma, they do not always behave as collisional fluids. The best motivation to study this comes in studies of the plasma in the solar wind and in the Earth's magnetosphere, where you can fly a satellite and not only measure electromagnetic fields, but also the properties of the plasma itself. This is a famous discovery of the plasma in the solar wind, which basically here, the axis is the ratio between the perpendicular and the parallel temperature of the plasma, perpendicular and parallel meaning with respect to the magnetic field, as a function of the plasma beta, which is the ratio between the thermal energy and the magnetic field energy. And you can see this line, which is 1, which would mean that the plasma is completely isotropic, is not a unique solution. The plasma can get almost any state, especially when it gets magnetized, as long as it doesn't cross these two thresholds, which are basically describing some instabilities where the plasma decides, okay, I cannot tolerate this anisotropy, I want to isotropize itself. So that happens through instabilities by exciting waves and so on. And the two other examples are that, the plasma is sometimes not always a guarantee, as I said. In the neutron star magnetosphere, it's self-produced. I'll go more into this physics. And the third example is that this magnetospheres like to develop very long extended current sheets. These are the regions where the magnetic field goes through zero. And those regions may control the large scales as well. For example, this tiny current sheet basically decides how many field lines that start on the stellar surface would not reach infinity. They would go out, come to this current sheet, and instead of going out, they would cross the current sheet, what we call reconnect, change their topology, and would not be able to escape. So how many of those field lines are doing that is specifically determined by physics at tiny scales inside this equatorial current sheet. So how do we model plasma physics on the computer these days is mainly through what's called the particle in cell method, which is basically a brute force approach where you have a three-dimensional computational grid. In every cell, you can have 3 components of the electric field, 3 components of the magnetic field. You can have charged particles flying around through the grid. They would experience a Lorentz force that is exerted by this electric and magnetic fields. The particles can prescribe the current. The current can be, again, a source in Maxwell's equations. And this whole system can be propagated through at every time step of your code. So comparing to more non-relativistic traditional applications, such as Earth's magnetosphere and the solar wind, in the relativistic world, you need things like radiation reaction force, meaning that if the particle emits a high energy photon, it has to lose its energy, substantial amount of energy, and this is taken into account in these codes. The photons that get emitted are sometimes not free to leave. If you get a lot of photons, they can start interacting with each other, producing electron-positron pairs, or they can interact with very strong magnetic field. If you get the photon traveling through a 10 to the 12 Gauss field, you can also produce electron-positron pairs. So all of this physics is these days included in many of the simulations with varying degree of precision, with varying degree of complexity, basically aiming to start understanding plasmas coupled self-consistently with radiation. This is an emerging topic in this community where we don't study just particle acceleration or large-scale plasma dynamics, but also radiation self-consistently embedded into the systems. So the theoretical approach that I try to follow for the systems is always to start with observations. And then the idea is that you try to come up with the best large-scale description of the system. And sometimes it would be a fluid description. Sometimes you can manage a kinetic description with a reduced separation of scales. And then you would go around and try to zoom into interesting regions, producing very localized, highly detailed simulations. In this case, this is a simulation of the small-scale current sheet in the neutron star magnetosphere, which then can be run for a very long time, for a lot of parameters, and produce things that can be compared with observations. In this case, this is a result producing a gamma ray spectrum of accelerated particles from a neutron star magnetosphere that can be directly compared with the gamma ray spectrum detected by Fermi from neutron stars. So this is it for this extended introduction. And then I would want to dive more closely into two topics. As I advertised, this would be rotation-powered neutron stars that we call pulsars. And then I will quickly go through some of the stuff for the black holes that the Event Horizon Telescope is seeing. So the pulsar is a rotating neutron star. This is a very dense object, roughly 12 kilometer size, of the mass comparable to 2 solar masses. The reason why they pulse is quite simple. You get this small spot in the surrounding of the neutron star radiating, and then the whole thing basically rotates around like a nice clock. And then when it points towards you, you see a pulse. Then it moves away, you don't see it. And then when it points towards you again, you see a second pulse. So it's not a mystery why they pulse. It's a mystery why they produce this emission in the first place. The basic physics that comes in here is quite simple. Basically, you can think of this as a unipolar inductor. This is this little experiment where there is a magnet, a battery, and the wire. So the battery provides voltage, and that runs a current through the wire. And then the magnet produces a magnetic field. And on this wire, you have a Lorentz force, J cross B, that wants to move the wire around. So the pulsar is sort of a thing in reverse. It spins by itself, and it has its own magnetic field. And then the result of that, there are currents circulating in the magnetosphere. How does that happen? Is because once you start rotating a magnet, you start inducing electric fields. Inside the star, the electric field in the frame of the star itself has to be zero, because the star is a very good conductor. But in the laboratory frame, by a Lorentz transformation, you would find electric field. And that would mean there has to be electric field outside of the star as well. So part of this electric field would point along the magnetic field. And what would happen is it would easily pull charges off from the upper layers of the neutron star, the normal sort of gravitationally supported atmosphere, with this very small difference that it's tiny scale. It's a few centimeters on the surface of a neutron star. And since the magnetic and the electric fields are so strong, basically they pull these charges out. They very quickly accelerate to energies comparable to 10 to the 7. They start moving along these curved magnetic field lines. And as they move on curved trajectories, they basically experience an acceleration. And acceleration by a Jackson textbook means that there is radiation being produced. This is the radiation that we call a curvature radiation. This curvature radiation can be depleted in very strong magnetic fields, producing electron-positron pairs. This electron-positron pairs then fill the surroundings of this neutron star, producing currents that modify the electromagnetic fields. And the goal is basically to understand how the whole thing would look like, and to understand how it emits radiation, which we now not only see in radio, which is how pulsars were discovered in the mid of 1960s, but all the way to this 20 tera electron volts that we now see from the Vela pulsar. The theoretical scheme was produced very early by Peter Goldreich and Julian in the end of 1960s, where basically they did not know yet about this pair creation physics. So they got to know about this very shortly after writing this paper. They thought of electrons being stripped off from the neutron star atmosphere, driving a current along the magnetic field lines. And the moment you have a current flying along the magnetic field line, you have a wire. The moment you have a wire, you will have a magnetic field wrapping around. This is the toroidal magnetic field, the field component out of this plane, which basically drives the whole thing. Once you get this toroidal field, the plasma also rotates. The rule of thumb is that if your central object is spinning, the plasma would always want to rotate with it together. So you get this corrotation, which is known also from a non-relativistic environment. And the vector product of electric and magnetic field produces a Poynting flux, which leaves out of the system. So the rule of the game is that you have this highly spinning magnet in the center. It loses its rotational energy by emitting this highly dominated electromagnetic wind. Okay? And moreover, we do know that this happens because we know that the sources are spinning down. They're perfect clocks, so we can monitor the period. We can see the period increasing with time, which means that the source is spinning down. And the rate of spinning down is precisely consistent with the magnetic field comparable to what I advertised, around 10 to the 12 Gauss. So this is a grand evidence of that the whole scheme that was proposed in the 1960s is more or less correct. So before computer simulations, it was very hard to do progress on these problems because basically the problem is highly nonlinear. And if you want to describe radiation, none of the sort of these theories on the list works. You need to go all the way to the kinetic physics. And that was only possible very recently. Around 10 years ago, we started to do the simulations using the particle and cell method, and I'm skipping basically a decade of research trying to construct this realistic magnetospheric models. This is a paper by Haik Hakabian, who was a student at the time working with me and Anatoly Spitkovsky at Princeton. This is a three-dimensional model of a pulsar that has a magnetic axis and rotational axis being aligned, so it doesn't really pulse, but it's a good starting point. We also have models of what we call oblique pulsars. These are harder to visualize in 3D. So that's why I'm showing you an aligned model. Here you see the black lines as our magnetic field lines. Some of them start on the star and close on the star. You don't see them behind this plasma curtain. You can see field lines starting on the magnetic pole, going out and extending to infinity, such that the Goldreich and Julian also pointed out. And then there are field lines basically crossing through this equatorial region where there is a dense plasma sheet. This is where the two magnetic field lines from two different poles come together, reconnect, and release their energy into the plasma. This, what we call a magnetization parameter, sigma, is the ratio between energy density in the magnetic field and the plasma rest energy density. You can think of this as basically an equipartition parameter. If you convert all of the magnetic field into the particles, the characteristic Lorentz factor that the particles would get would be comparable to sigma, because then the thermal and kinetic energy of the plasma, which will be given by this expression that I'm trying to circle, would be equal to the energy density in the magnetic field. So basically what happens is that magnetic fields fully give up on their energy, convert it into particles. And since the fields are so strong, they immediately radiate their energy away, the synchrotron radiation, and we can work out the theory, and that would lie in the gamma ray band. So this is an example of a light curve that we can produce, because basically we have these particles, each of them is radiating. That means we can collect light coming from all of these particles, and that would show up as an observer sitting where you would be sitting, a light curve like this, with two characteristic peaks, which is very consistent with what Fermi satellite discovered around 10 to 12 years ago. So basically, the geometry of this magnetospheres is fully consistent with what we see at highest energies. And arguably, this Fermi discovery was essential to drive research into these magnetospheres, because we found out the major energy budget that comes out from neutron stars in this high energy band. What had been seen before was only the radio, and the radio is a tiny fraction of everything that goes on in the systems. And when you are trying to describe something of order of 10 to the minus 4 of the whole thing going on, that gets complicated. What gets irradiated in gamma rays is basically 10% of what goes out in the form of this Poynting flux dominated wind that goes away from the neutron star. So I'll not go into too much details. These are some of the examples of the light curves for particular viewing angles onto the pulsar, comparing them with Fermi. Recently, we have been working on predictions of this physics for tera-electron volt emission in line with the detection by Hess from Vila. So we have predictions for which pulsars have to be tera-electron volt sources. And this is very exciting with the Cherenkov telescope array coming online within 5 years from now. So as I move on, I would like to quickly talk about the radio emission, which is the original enigma of pulsars. And the enigma here is that the radio emission is not just your usual thermal emission, or not even the unusual non-thermal emission. What comes here is what we call coherent emission. And why do we know that this is coherent? And I'll explain in a second what this means. Is because if you want to convert a radio flux into an effective temperature of a hot black body that would be sitting and radiating, you would get something around 10 to the 30 Kelvin in some cases. And in examples from FRBs, fast radio bursts, you can reach all the way to 10 to the 40 Kelvin. So obviously, none of the thermal or even energetic particle distribution cannot do it unless somehow they manage to arrange themselves such that they don't almost emit individually, but manage to emit together. So how does that happen? Is that the electric field emitted by one particle gets in phase with the electric field of all other particles, And then you multiply not the intensities of the radiation, but you add up the electric fields. The moment you add up electric fields, you get an n square effect, where the n is the number of particles. The total intensity will scale quadratically as you increase the number of particles. And this has to rely on some very organized plasma behavior that has not been discovered using analytical techniques for a very long time. And the reason is basically we did not know how the plasma structure in this magnetospheres would look like. There are some lines of evidence that has been known for quite a while. This radio beam is concentrated around this field lines that do escape to infinity, localized around the magnetic pole. There are arguments of this given by the total width of the radio profile that you see from a pulsar. It's quite short, so there is a small patch in the magnetosphere radiating. And the other line of evidence is more involved. I'll not go into this into too much details, but basically from the behavior of the linear polarization of this high brightness temperature electromagnetic radiation, you can infer the geometry of the magnetic field. And it turns out it's fully consistent with the magnetic field sort of sweeping through the magnetic axis as a line of sight passes through you. So that is very consistent with a small cone of field lines near the pole emitting the radiation. So what we've been able to do, I think we're able to come up with a realistic simulation-motivated emission mechanism for this physics. And what we uncovered is that the production of electron-positron pairs in the sources is not a steady process. So what I told you in the beginning, you strip off particles, you accelerate them to high energies, they emit photons, photons decay, all great, you produce electron-positron pairs. Well, this thing doesn't last for a while, right? The moment you produce new electron-positron pairs, they start shortening out the electric field. Positrons go one way, electrons go the other way, they screen the electric field, none of the new particles are accelerated. So you need to wait until all of this plasma clears out from the acceleration region, and you can get the process going on for the next time. So what you see here is a very localized simulation. This is the surface of a neutron star. You rotate it out of the simulation plane. This produces electric fields. The magnetic field points vertically here. This is the plasma density in the simulation, and you see basically big clouds separated by quasi-vacuum regions. That means when at some point the number density of the plasma became high, it fully screened the electric field, no new particles were produced, and the system was stopped for a while. So once that happens, in the process of screening the electric field, you can monitor what happens with electric and magnetic fields in the system. So you start with this very strong coherent electric field of a given color, in that case negative. It was accelerating electrons out from the stellar surface. It basically starts ringing at all frequencies. This is the moment you drop plasma into it and the electric field starts oscillating. And what simulations, in particular multidimensional simulations, discovered is that in the process of doing so, the plasma is ringing not only in the electric field, but also in the electromagnetic field component. You see this electromagnetic waves being created as this electric field screening is going on in these clouds of electron-positron plasma, and they can propagate outwards. So I'll not go into too much details because I do want to cover something about the black holes. But the rule of thumb is basically we can now predict the luminosity of these things. And moreover, we can get a hint of the morphology of the radiation beam. There are many things that are still not explained. The sources are very rich. The phenomenology accumulated over 60 years is quite vast. So there is lots of things to be done. But what my hope is that this mechanism gives foundations that people can build on more and more. And moreover, it's been confirmed by multiple simulation codes, including global simulations that Ashley Bransgrove at Columbia performed 2 years ago. So this is it for neutron stars. You could ask me about any other types of neutron stars if you're interested, but I would go to black holes. And in particular, I would like to focus on these black holes that the Event Horizon Telescope observed. And why I'm focusing just on 2 black holes while there are so many more in the universe is, of course, because they've been observed by EHT, but also they host these environments which are most promising for plasma studies, because the plasmas around them are also highly collisionless and highly magnetized. The magnetic field around these sources is in contrast to 10 to 12 Gauss. In the previous chapter is around 100 Gauss, so it's much weaker. But the size of the Larmor radius of the particles that are orbiting around the magnetic field are much, much smaller compared to the size of the central black hole. And it's orders of magnitude. There are at least 1 billion ratio between the size of the black hole and this tiny motion of electrons around the magnetic field. The plasma is collisionless, the density is low, temperatures are high, and they have to do the same plasma physics that I've been advertising throughout this talk. How do we see them apart from EHT is that the black hole in our own galaxy is flaring roughly a few times a day. You can expect a flare roughly every 6 hours or so. They're flaring in near infrared and in X-rays, and the black hole in M87 is also flaring in tera-electron volts. And in contrast to flaring a few times a day, this beast flares once a year, which is roughly consistent with the black hole being 1,000 times bigger. The bigger the black hole, the bigger the light crossing time across the black hole. So that means all time scales have to be roughly 1,000 times more inflated. And that's roughly consistent between the two flaring sources. The big scale picture, again, was produced by Roger Blanford and Roman Znaik in mid of 1970s, which basically works on the same idea that was applied for pulsars. In a pulsar case, you had a rotation of the central object, a central magnetic field, and the spin of that was producing electric fields. In this case, what happens is that there is no rotation of anything solid because the black hole is not a solid body, but there is a frame dragging, the rotation of the space-time itself that winds up this magnetic fields. And then basically the story is very similar. As you wind up this magnetic field, you would produce electric fields. You would drop a charged particle inside this region. It would accelerate to high energies, collide with a photon that is produced by a matter accreting onto a black hole. And that would create you a high energy photon, this one, that can then collide with a soft photon radiated by the accretion disk, and you produce an electron-positron pair, and you can create a pair-dominated outflow from the supermassive black hole. So very similar story to what was done for pulsars. These things are now modeled in details using magnetohydrodynamical simulations. This is one of the state-of-the-art three-dimensional simulations. In this case, this has been averaged over the azimuthal direction. So you can see these field lines that are extending over the accreting plasma. This is the plasma in the jet, dominated by the energy density of the magnetic field, throwing out particles to infinity along these field lines. And the problem is basically quite similar to pulsars, is that the plasma is actually collisionless, so we don't even know how applicable MHD is in describing the systems. And inside jets, you can worry about things such as pair production and the actual density of the plasma that is not guaranteed. It has to be created self-consistently. So I'll not talk into details. We have a study that covers creation of plasma around the black hole in this paper led by Benjamin Krinkond a few years ago, which uncovered physics similar to what happens around the neutron star itself. So again, the approach here is to try to come up with a big scale picture, zoom in on small scale things, try to describe acceleration of the particles, and that would give you the photon spectrum. This model in particular, I will go into a few details later, was geared specifically to understand this hotspot motion described by gravity. The bigger scale picture was produced when Bart was a postdoc with me at Flatiron, where we basically ran the biggest possible MHD simulation available at that point, and it uncovered interesting details. Instead of permanently accreting, this thing undergoes state transitions. It accumulates magnetic flux until a certain point, and then it basically decides to reject flux. And the moment it rejects flux, it starts accumulating it again, and then it rejects it again, and the whole process continues. If I would run this longer, I would get the sequence of accumulation and rejection of the magnetic flux events happening sort of quasi-periodically. So how does flux rejection actually happens? If you look at small scales, you start to see a reconnecting current sheet. So this is the region where the plasma density gets very low. The field lines in the jet are opposite to each other. And basically what happens is that you get these field lines in the jet, they accumulate, reconnect, they change the topology, they start looking something like that. And this whole thing gets ejected towards the accretion disk. So it basically removes the magnetic field of the black hole in order to give the plasma room to start accreting again. And as that happens, you can keep the system going in a sort of this blurry steady state that oscillates around. So this has been great. And the next steps were obviously to try to understand how this would change if this would not be a magnetohydrodynamic collisional fluid, but would be an actual collisionless plasma. And the rules of the game here is that there are some large-scale effects that this approximation can violate. One of them, as I advertised, the dynamics can become complicated when the pressure tensor of the plasma is not really isotropic. The plasma behaves differently across and along the magnetic field, motivated by the solar wind observations. But also the rate at which the plasma can process pushing this magnetic field through the zero turned out to be different. So depending on how many physical approximations you do on the small scales, the rate at which the plasma would want to eject the magnetic flux from these regions would be quite different. And the difference is roughly a factor of 10, and that can be significant for large-scale long-term dynamics of the accretion flows. So we've been able to test this using a very reduced scale separation particle and cell simulations in general relativity that Alisa Galishnikova, a PhD student at Princeton, led and published in roughly a year and a half ago, where we basically directly compared MHD simulations within this collisional approximations with fully particle and cell simulations. And we've been able to identify and report differences which are basically consistent with this logic that I tried to advertise. If you monitor the magnetic flux on the black hole, the flux is accumulated until a certain point, and that gets rejected as the flux on the black hole is dropping. And this drop happens differently for the fully collisionless simulation and the fully collisional fluid simulation. So as these things are different, if you would be able to run them long-term, we expect also much longer-term differences. And I can go into details of these models if anyone is interested. They can also take an effect on the images that the Event Horizon Telescope is observing. This now goes towards the fact that the pressure tensor of electrons may not also be completely isotropic. If you remember, the synchrotron emission is basically peaked if the electron goes exactly perpendicular to the field. If you get more electrons moving along the field, for example, than the moving with large pitch angles with respect to the field, then the emission from the ensemble of electrons would be quite different. So basically, it would shine uniformly across all pitch angles. And that's what we've been seeing in this post-processed result, where we assume that there are more electrons going along magnetic field lines with small pitch angles rather than with large pitch angles. And we're looking forward to test this with new observations with the Black Hole Explorer. My dream is that we can convert EHT into a plasma experiment as expect to a gravity experiment. And there is a lot more to explore on this front as well. So I think in spirit of not running far on time, I would just advertise that we have many observational predictions of how these things may look like. Probably the biggest prediction is that we expect the image to dim at some point. This is a post-processed emission radiation map from accreting black hole in M87. And at some point, you just see that the ring becomes dimmer. It's bright at this point, and then at some point, it becomes dimmer. And this happens exactly at the moment where the magnetic flux from the black hole is rejected. So at certain times, you would expect this thing to dim, and we have predictions that you may expect a high-energy flare happening exactly at the same time. So if you could organize a multi-wavelength campaign centered around this point, which would be available if you have a movie of the image, and this would be available with the new generation Event Horizon Telescope, then you could test all of these predictions coming from these simulations. We already are involved with something interesting with the James Webb Telescope, which for the first time observed the mid-infrared flares from the galactic black hole. And basically, the story is that it ruled out a decade-long consensus that the spectrum of these things is steady. Even during one flare, the spectrum was changing, which was consistent with very strong magnetic fields, cooling down electrons and affecting the spectrum. So there's lots of things happening both observationally and theoretically here. I would argue that the future is even brighter. There will be a lot happening in the radio band. DSA 2000, the deep synoptic array with many antennas, would cover the big fraction of the sky. It would observe phenomena that we probably did not see before. Maybe if we are lucky, we could see radio precursors to neutron star mergers if we actually observe more than one available right now. square kilometer array in the southern hemisphere would be much more sensitive and would see practically all the pulsars in the galaxy, at least all the millisecond pulsars. As I said, the Event Horizon Telescope will be upgraded with new baselines across the globe. They would own them for real, so they could record movie. And this Black Hole Explorer would basically be a mission on an orbit around the Earth and would be having a larger baseline and more sensitivity to be able to record an image at higher resolution. Much more will happen at higher frequencies, at CTA, with TeV, with new neutrino detectors, and at highest frequencies. LASSO in China is now seeing photons all the way to 1 peta-electron volt, and this uncovers new sources and new phenomena that we're not thinking about. So in my conclusions, I would just like to say that I think many of the long-standing neutron star problems are now addressed with numerical simulations, more or less directly. There is a lot more going in physics of accretion flows into supermassive black holes in the centers of galaxies, and I think the future is even brighter. The future is bright for both observations and for people who want to go into this field and explain them with first principle physics. Thank you so much.